uh, this is week 2. Okay, this is week 2, and I'll be continuing with our lecture for week 2, which is uh, diffusion. Okay, diffusion. So I'll be covering until on steady state. Okay, all right. Okay, now, okay, students. Just a quick recap. There is also one small error which have been raised by one of the students here. If you look at lecture 1, slide page 28, specification of composition. Okay, please take note of this. Okay, there is a mistake in the slide where the formula of converting atomic percentage to weight percentage for C1, okay, supposedly this A2 is A1, okay, not A2. Okay, please change this and take note of it. Okay, supposed to be A1. Okay. It's okay. Yes, only for C1, yeah. Only for C1. This A2 is actually A1. Okay, C1, A1, where C1 is atomic percentage and A1 is atomic weight. Okay, so it is for the first element. Okay, all right. Please, what they call, change in your slide and take note of it. If there's any student, any of your friends who is not here, please let them know. Okay. All right, now let's continue with our lesson. Now let's talk about diffusion. Okay, last week we learned about imperfections in solid, where you have impurities in a solid. I did give some example on alloys. Now, for today's topic, it is related to imperfections of solid, but in a broader spectrum. I'm going to discuss about diffusion. How does a diffusion works? Okay, let's, for example, all right, you are, just imagine you are in a room and there is a lot of mosquitoes going around, and you took an aerosol spray and spray towards a particular point inside a room, for example, underneath the table. All right, after a moment, after about 1-2 minutes or 5 minutes, let's take it 5 minutes then. Okay, you can have the sense of smell of the whole room being filled with aerosol. So that is the main what they call that definition for diffusion. The aerosol spray diffuses towards the whole room. Same goes to smoke. We are talking about air now. Okay, same goes to smoke. And if let's talk about water then. Water. Okay, you have a cup of water, clean water, and you Uh, take 1 tablespoon or 1 teaspoon of coloring, water coloring, edible water coloring, for example, cherry. Okay, you add those coloring inside the clean cup of water. After a few minutes, the whole cup of water turns into red. So the coloring diffuse inside the molecule of water. So that is diffusion. Now, for this topic, I'll be discussing with you how does diffusion happens, under what condition, and what are the laws that governs diffusion. Okay, please take note of these. This is very important. Okay, now we will be covering the introduction part for today's lecture, rate of reaction and diffusion, and the types of mechanism. Okay, diffusion mechanism involved. There are two types: vacancy diffusion and interstitial diffusion. And then we will be covering steady state diffusion, which is Fick's first law. And I'll be giving you some shallow introduction on non-steady state diffusion, which is Fick's second law. Okay, on this coming Friday, we'll be go detail on this Fick's second law and also factors that influence diffusion. For today's lesson, I'll be concentrating more on this part with a brief introduction on non-steady state diffusion. Okay, now rate of process in solid. Okay, if you look here, many processes concerned with the rate at which atom move in the solid state. For example, imagine in a solid state, all right? Imagine in a solid state, you have an arrangement of atoms, all right? Let's say the atoms are colorful. Okay, let's see the atoms are colorful. For example, you have copper here, and then you have nickel here. After some time, as I mentioned to you earlier in this today's lesson, where it diffuses, the aerosol diffuses the whole room. This what happens. All right. When we look into solid, copper mixed with nickel in a randomly arranged manner. But the word random, you should be aware of. There are some rules and clauses that a material should follow so that it diffuses correctly. That's what I'm going to discuss with you today. Okay. Now, reaction occurs in solid state, resulting in a more stable atomic arrangement. Highlight this, students. Diffusion happens so that the atomic arrangement becomes more stable. Diffusion happens. Okay, let's talk about the example, mosquito and room example. Okay, mosquito aerosol. Okay, when you spray mosquito aerosol underneath the table, the whole room smells aerosol, right? So that means that once the whole room filled with aerosol, it means that steady state have occurred. Okay, there is no diffusion. The diffusion rate have decreased. So it means that it results in a more stable environment in the case of mosquito. All right. In a case of atomic arrangement, diffusion resulting in a more stable atomic arrangement. Okay, please take note of these. All right. Reacting atoms must have sufficient energy to overcome activation energy. Okay, these are the first rule. This is the first rule. All right. Diffusion don't happen just like that. It needs to have sufficient energy to overcome activation energy barrier. It means that each atoms need to have enough energy to overcome the energy barrier. Okay. Now, one of the crucial factors that affecting the energy barrier is temperature. Write it down. Temperature, okay. One of the crucial factors that affects the activation energy for atoms or molecule is temperature. Okay, at a given temperature, okay, let's say at a given temperature, present room temperature, not all atoms have activation energy. It should be supplied to them. Okay, you have a lot of atoms, different types of atom arrangements, and when you induce temperature into it, not all atoms get the energy uniformly. Okay, that's what they're trying to say here. Okay, now let's look at this graph. Okay, EP is energy product, ER is energy of reactants. Okay, this is your energy of reactants is over here, and E asterisk is activation energy level. Okay, and the difference between activation energy level and ER is activation energy. These are the energy required for an atom to diffuse into neighboring atom or neighboring planes. Okay, and this is the energy released due to the reaction. Once it moves, it releases energy, and you have your products, the final products. Okay, here, as temperature increases, more and more atoms acquire activation energy level. Highlight this. General rule of thumb says that as temperature increases, more and more atoms acquire activation energy level. Okay. Probability of finding an atom or molecule with energy greater than average energy of all atoms molecules are given by this. These are the formula. Look at here. Changes in activation energy minus average energy. Okay, the probability is epsilon negative, which is direction. Okay, activation energy minus average energy divided by K is your Boltzmann constant and T is your temperature in Kelvin. Okay, so that is the rate of process in solids. Okay, I'm going again. Reaction or diffusion occurs in solid state, resulting in more stable atomic arrangement, right? And for it to happen, the reacting atoms must have sufficient energy to overcome activation energy barrier. Okay, therefore at a given temperature, not all atoms have activation energy. It should be supplied to them. And also, as a general rule of thumb, as temperature increases, more and more atoms acquire activation energy level. Okay, so that is the rate of process in solids. Okay guys, now let's talk about diffusion, right? Diffusion is a phenomenon of material. Okay, I'm repeating these. Diffusion is a phenomenon of material or mass. Okay, let's talk about mass. Transport by atomic motion. Okay, diffusion is atomic movement within the atomic structure arrangement. So try to imagine you have a plane. Okay, you have a plane, a linear plane, 2D linear plane, and you have lots of atoms. So within atom arrangement, those atoms move within themselves when there is an increase in temperature, and not all atoms move together. Only certain atoms that achieve higher activation energy that can overcome the barrier energy can move. Okay, so these nodes by the temperature vary with temperature and also kinetic energy. And one of the application we use for diffusion is heat treatment. Almost all the heat treatment that an engineer does to a material is diffusion. Okay, the examples that I can point out is movement of smoke particles in air, which is very fast. It diffuses very fast. Same goes to the example that I've quoted earlier, mosquito. And then movement of dye in water, relatively slow. The example I've mentioned to you just now about the coloring, food coloring. And solid state reactions, movement in solids, which is very restricted movement due to the strong bonding. Okay, all of you should know that solid have a very strong bonding, right? So in order for diffusion to occur in solid, you need to have a very high activation energy. Okay, and for you to have a very high activation energy, you need to increase the temperature of the solids. Okay, so example of diffusion. You have copper, we have nickel. Okay, before diffusion, initially it is like this, right? After some time, okay, when you mix both together, the concentration of copper and concentration of nickel mixed up to have a randomly arranged atom. Okay. Now, I've given you the definition of diffusion. Now, got how there are two types of diffusion. The first one is self-diffusion, and the second one is impurity diffusion. For this topic, for lecture 2, I'll be concentrating more on impurity diffusion. Please take note of this. Okay, I'll be concentrating more on impurity diffusion. Okay, now let's talk about self-diffusion. Now, self-diffusion is an atomic migration in pure metal ore of the same type. Okay, now for self-diffusion, okay, highlight this. For self-diffusion, it is the movement of atom of the same type in a material. For example, you have a solid, and you are heating up the solid, pure metal. Okay, you are heating up aluminium, pure metal. At certain temperature, let's say 600 degrees Celsius or 700 degrees Celsius, the atom move by itself, diffuse among themselves. Okay, that is self-diffusion. Impurity diffusion happens, diffusion of atoms of one metal into another. Impurity diffusion happens when there is an interstitial voids or spaces between the atom arrangement and you have a foreign particle diffusing into the host particle. Very similar to the imperfections of solid, which we have covered last week. Substitutional. Okay, interdiffusion. Here. All right, types of diffusion, self-diffusion. All atoms exchanging position are of the same type, right? Pure element. You have a void here, and it's just changed the voids. So it moves around. Move around because it has attained sufficient energy, which we call that as activation energy. Now for interdiffusion, impurity diffusion, right? Okay, you can highlight this, impurity diffusion. There is a net drift or transport of atoms from high to low concentration region. Okay, now for this example, okay, for this slide, I'll quote the same example that I've quoted earlier, which is the mosquito, right? Now, you spray underneath the table, right? You spray underneath the table and the concentration of aerosol underneath the table is very high. Concentration of aerosol around the room is low. So diffusion happens from high concentration to low concentration. That is what happening. That is what we call that as interdiffusion. Okay, there is a net drift or transport of atoms from high to low concentration. Okay. Any questions so far? Students, any questions so far? Hello, can you hear me? Anyone? Okay, all right, that's good. Okay, all right. So just a quick recap. Let me see. Okay, now. So now you know there are two types of diffusion, which is self-diffusion and impurity diffusion, and the definition of diffusion. Now, diffusion mechanism. All right. For an atomic diffusion to occur, it must meet two conditions. Okay, these are the conditions. There must be an empty adjacent site. Okay, there must be an empty adjacent site. For example, empty adjacent sites. Or there must be a voids. Okay, these are the voids over here. These are the voids. Interstitial space between atoms. Okay, and okay, these are the first rule. There must be an empty adjacent site. The second rule is the atom must have sufficient energy to break the bond with its neighbor atom and then cause some lattice distortion during the displacement. Okay, so you have all the atoms here. This atom must have sufficient energy to break the atoms, okay, to break the atoms of the neighboring atom and move towards the other region, so that this will create a disruption in the lattice structure. Okay, so for the atom to attain sufficient energy, the main factor is temperature. Okay, do you understand? I'm going slow and steady, guys. Can you understand? Okay, that's nice. All right, now guys, let me see. Interstitial flux. Okay. Okay, now I'm giving you 5 minutes. Try to digest this. If you have any question, ask me, and then we continue with the types of mechanism. Okay, I'm giving you 5 minutes. Try to digest the slide that I've discussed with you. If you have any question, then we take it up from there. After 5 minutes, we start with diffusion mechanism. Okay, try to digest now. All right. Any other factors beside temperature? Yes, there's a lot of factor actually, but the main crucial factor is temperature. Okay, for the factors, I will be discussing with you next week. Sorry, this Friday. Where is it? It's over here. Factors that influence diffusion. Okay, good question. Okay, so where is the activation energy level? This is the activation energy level here. Okay. Yes, the dot line. Okay, once the atom reaches activation energy level, it means that diffusion can happen. Okay, once diffusion is happening, it loses its energy to become steady state, and then it becomes a new product, which is what we call that as more stable atomic arrangement, because energy is being transferred. Okay, other students, can you understand? I'm going slow and steady like diffusion. So the previous chapter is talking more on. So the previous chapter is talking more on diffusion in solid. Yes, Diffusion in solid in terms, I'm giving you an introduction on imperfection in solids. Imperfection in solids is different than diffusion. Imperfection can happen due to stress as well. So diffusion is a part of imperfection. You can put it in that way. You cannot say that diffusion is, yeah, okay. You got it right? Lower Wang Hang. Okay, okay, all right. I'm happy that you can understand. That is my main objective. Any other questions? Okay, I'll give you 5 minutes. Okay, try digest. Maybe we resume at 2:32. Okay, okay, let's make it 2:35 then. Okay, 2:35, 5 minutes. Okay, adjacent site, students, adjacent site means site beside the atom. Yes. The average energy E in the probability formula is equal to EE. Teo Chian Zan, I don't understand your question. The average energy E in the probability formula equals to E. Or yeah, yes, correct. E asterisk is the activation energy, E is the average energy, yes. Okay. All right, we shall continue now. Just a quick recap. Okay, we are in a topic diffusion. All right, I've discussed your introduction, rate of reaction and diffusion, and what is the meaning of diffusion, right? Types of diffusion. Okay, now, and also the conditions that diffusion will occur, right? Okay, now um, the mechanics or the science behind the process of diffusion. Okay, I never discussed you the process of diffusion is there are two types. Okay, we have vacancy diffusion and we have interstitial diffusion. These are the mechanism or the process of diffusion. Don't get confused. There are two types of diffusion, which is self-diffusion and impurity diffusion. For mechanism or process, there are also two types, which is vacancy diffusion and also interstitial diffusion. Okay. For vacancy diffusion, the definition is interchange of an atom from a normal lattice position to an adjacent vacancy. Okay. Vacancy diffusion occurs only when there is an empty space between the surrounding atoms. For example, when there is an empty space within the surrounding atoms. Okay, which translate to self-diffusion. Okay, interstitial diffusion involves atoms that migrate from an interstitial position to a neighboring interstitial site that is empty. Okay, having said that, interstitial moving from voids of spaces between atoms to another voids or spaces between atoms. Okay, got it? So if you look at this part over here, the blue atoms remains fixed. The red atom fills the void or interstitial spaces between the blue atoms. Okay, these are the types of mechanism. So there are two types. Okay, the first one is vacancy diffusion and the second type is interstitial diffusion. Okay, for vacancy diffusion to happen, you must have a empty space. Okay, interchange of an atom from a normal lattice position to an adjacent vacancy. For interstitial diffusion to happen, it involves atom that migrates from an interstitial position to a neighboring interstitial site that is empty. Don't get confused by vacancy and empty. Vacancy is an empty space where there is no atom on that plane. Okay, and this empty reflects to the interstitial voids between atoms. Okay. All right, there's a question. The yellow atom uses which diffusion? The yellow atom is impurity diffusion because it is different material. Okay, so it's a blend of self-diffusion and also impurity diffusion. Okay, and also don't get confused. Both can happen at the same time. That is the practical manner. Okay, you cannot relate this atom only happens in vacancy, these atoms, this material only happen in institutional diffusion. No. Okay. All right, now let's talk about vacancy diffusion in more in depth. Now, for vacancy diffusion, which is substitutional diffusion, see, substitutional diffusion, degrees of diffusion depends on the number of vacancy that presents. Highlight this. Okay, highlight this. Degrees of diffusion depends on the number of vacancies that present, and the motion of vacancy would be in the opposite direction of the correspond atomic diffusion. Okay, the motion of vacancy. So this vacancy moves here, this atom moves here. So there is a void here. I mean, there's a vacancy space here, not void. Okay, void is this. This is voids. Okay. All right. Repeating again, for vacancy diffusion, the degrees of diffusion depends on the number of vacancies that are present. If there is a lot of vacancies present, the degree of diffusion increases. Okay, can you see? Now we are going much more in depth. Okay, and also the motion of the vacancy would be in the opposite direction, correspond to the atomic diffusion. Having said that, the motion is opposite. Let's say the atom travels from here to here, the motion of vacancy travels from here to here. Okay. Now, for interstitial diffusion, more common with smaller size such as hydrogen, carbon, nitrogen, and oxygen. Small atom fits in interstitial sites. This is logic. Highlight this. For interstitial diffusion, it is more common, occurs with a smaller size atom, mixture of atom, such as hydrogen, carbon, nitrogen, and oxygen. This is non-exhaustive. All right, more rapidly and frequently than vacancy diffusion. Okay, please highlight this. Interstitial diffusion happens more frequently than vacancy diffusion because of these reasons. Interstitial atoms are smaller and more mobile. So imagine you are driving a car and you are stuck in a traffic light. Motorbike can sweep past through you. So the motorbikes are interstitial small atoms which is diffusing around the roads. Okay, let's put it in that way, easier for you to understand. Right? And more empty interstitial position than vacancies. There's a lot of voids in a plane than vacancies in a plane. Vacancies are very rare, but there are a lot of voids in a plane. Okay. Now, we have covered the mechanism of diffusion. Now, let's discuss on the calculation involved behind the mechanics of diffusion. The key term that you need to know is diffusion flux. Okay, the key word that you need to know is diffusion flux. Now, diffusion flux J, diffusion flux J is mass. Okay, the mass. Okay, let's talk about mass. M, amount of mass M diffusing through and perpendicular to a unit cross-section area of a material per unit time, which is essentially the rate of mass transfer. Okay, that is diffusion flux, rate of mass transfer. What is diffusion flux? Is a rate of mass transfer. So J is mass divided by the cross-sectional area times with the diffusion time. And this is the rate of mass transfer. 1 over A times with rate of change of mass over time. Del M del T. And the unit for diffusion flux is kilogram per mass square S. Meter square S. Okay, kilogram per meter square S, or atoms per meter square S. Okay, please write this down. This is diffusion flux, and the definition for diffusion flux is rate of mass transfer, which is mass M diffusing through and perpendicular to a unit cross-sectional area of material per unit time. Okay. Well, let's see, there's a question here. Okay, so yellow atoms is vacancy diffusion, red atom is institutional diffusion. No. Yellow and red is interdiffusion, impurity diffusion, because it is different material. Okay, just that the red move, this has self-diffusion because maybe the activation energy for yellow is large, something. Okay. All right. Okay, guys, please write down this formula. Diffusion flux, and we continue. Now, guys, the mathematics behind diffusion flux. Okay, we have two types. All right, two types of mechanism, which is vacancy diffusion and interstitial diffusion. Right. Now, for diffusion flux, for diffusion, you have two types of diffusion, which is steady state diffusion. We are talking about analysis. For analysis, we have two types. The first one is steady state diffusion, and the second one is non-steady state diffusion. Okay. Now, for steady state diffusion, the key point is diffusion flux does not change with time. This diffusion flux does not change with time. It is fixed. Highlight this. And then it is proportional to the concentration gradient. The higher the concentration, the more higher the diffusion flux. Okay, bear in mind, this applicable to steady state diffusion, which is under fixed first rule. All right. And this is your concentration gradient, rate of change of concentration over rate of change of the values or distance. Okay, concentration of A, which is higher, minus concentration of B, which is lower, over distance of A, which is higher, distance of B, which is nearer to the surface. Okay, this is concentration gradient. All right, now let's see this in a broader spectrum. Now let's say over here, the pressure of gas A is higher. And then you have a barrier, thin metal plate. Over here, the pressure of gas B is low. So as I mentioned to you earlier, diffusion happens when there is a changes in concentration. Okay, try to recap back about the aerosol spray, which I mentioned to you earlier. You spray underneath the table, the concentration is higher, and then it starts diffusing to the whole room. Same ideology applies here. All right. The concentration of PA here is higher, and the pressure is higher, and here the pressure is low, and it is constant. When there is a changes in concentration in terms of pressure, diffusion happens. So gas at pressure A tends to travel, diffuse through thin metal plate and comes here. And the definition for diffusion flux is mass M diffusing through and perpendicular to a unit cross-sectional area of material per unit time. So you need to take the calculation of cross-sectional area of this thin metal plate, area A, per unit time. Okay, the concentration profile shows the concentration C versus position within the solid X. Okay, XA and XB. Let's say this is XA, this is XB. The slope at a particular point is the concentration gradient. So the slope at a particular point is the concentration gradient. At CA, concentration here is high at XA. Okay, once it diffuse, the concentration of CA becomes lower towards the end of your thin metal plate, which is XB. Here the concentration of B is higher. So this is the concentration gradient. Okay, digest this, try to digest this. Now for steady state diffusion, okay, diffusion flux, okay, for steady state diffusion flux, please write down this formula. Over your tutorials, I'll be asking question on this. So put this into practice, please write down this formula. So for steady state diffusion, the diffusion flux J is negative direction of diffusion times D. D is the diffusion coefficient in meter square per second times with concentration gradient, which is del C over del X, which is this concentration of A minus concentration of B, which is higher concentration minus lower concentration, divided by the distance near to A minus distance near to B. Okay, please take note of this. From this, you know that concentration gradient is the driving force for the diffusion reaction. Higher the concentration gradient, the higher the diffusion reaction. The magnitude of D indicates the diffusion rate. This is the diffusion coefficient. Okay. Any questions, guys?
So the negative is because of the
Direction.
high concentration to the low concentration, right?
Yes, yes, yes.
Right.
Direction.
Thank you.
Let's say if there is a more higher activation energy, you can reverse it. That's why there is a direction. Okay, good. Any other questions, guys? Any questions? Try to digest the table. I mean, sorry, the graph. Okay, good. All right. So that is about steady state diffusion. Steady state diffusion. Now, let's talk about non-steady state diffusion. Okay, I did mention to you steady state diffusion is independent of time. It does not change with time. For non-steady state diffusion, time comes into consideration. Okay, non-steady state diffusion, the diffusion flux and the concentration gradient at some particular point in a solid varies with time. So varies with time means you need to take the average. Okay, for example, at time T1, which is shorter time, the concentration gradient is in this profile. At time t2, the concentration gradient at this profile. At t3, the concentration gradient at this profile. So these are non-steady state diffusion. Okay. This happens with a net accumulating or depletion of the diffusion species resulting. Okay. For non-steady state diffusion is where it involves most practical diffusion situation. Almost all the diffusions that is happening naturally and also synthetically happens in non-steady state diffusion. Okay. All right, let's see what this says here. The figure on the right shows the concentration profile for non-steady state diffusion taken at t different time. Okay, t1, t2, and t3. All right. Okay. Okay, guys. So the difference between non-steady state and steady state. For steady state diffusion, we call that as fixed first law. It does not change with time. For non-steady state, it depends and varies with time. The concentration gradient varies with time. Okay, and we call that as fixed second law. Okay, you have two laws. The first one is fixed first law reflected to steady state diffusion, and fixed second law reflects to non-steady state diffusion. Okay, fixed second law says that if the diffusion coefficient is independent of composition, the time rate of change of concentration is proportional to the second derivative of concentration. So your formula will have second derivative in the concentration curve. Okay. I'm repeating again. Fixed second law says that if the diffusion coefficient is independent of composition, the time rate of change of concentration, okay, time rate of change of concentration is proportional to the second derivative of concentration. So it means that the concentration varies. Okay, the concentration profile varies with different times. For example, for non-steady state diffusion, I'll give you a simple example for your understanding. Okay, remember the first example which I quoted to you, mosquito. Okay, you are in a room, mosquito bite, and you spray once under the table. Okay, that is steady state. But after some time, you're still having the mosquito nonsense going around your room. So you keep on spraying at the same place through a different time. So that is non-steady state diffusion. Put that in that manner. Okay, take that in that manner. All right. Okay, guys. We are now at slide 20. Okay, we need to save this for next. This coming Friday. Okay, guys. Any questions until now? Any questions until now? Can you understand? So the fixed first law is ideal and the second is practical. No, no, no. It is not ideal. Sometimes there is also non-steady state diffusion happens. Okay, like once you kill the mosquito, you are not going to spray again, right? So that is steady state. Okay, guys.
So steady state diffusion does happen in real life, right?
Yes, yes.
All right.
It is not theory, it is practical. Okay, any other questions? Any other questions, guys? Okay, there's one more student who haven't signed the attendance. There's only 51 response. There are 52 students in this class today. Please write down the sign in the attendance for those who haven't signed. There are only 51 responses. In this meeting, we have 52 students. Okay, any real life example of non-steady state? This is a tough question you have asked me. Any real life example? So I thought we are having 2 hours class. Yes, 2 hours class, but during online lesson is more of a jam. I mean, I've tried to contain the class as short as possible because a lot of what they call that hours spent on online, I don't think it is effective. Is it okay with you? Because for 2 hours, I can cover the whole lecture too. Then you don't have class on Friday. But I had to, since Friday we need to have class, so I need to have class with you, okay? So that's the reason why I try to break it into two. Guys, for wait, don't reply. For Qua Wen Hun, any real example of non-steady state? I can't think of. Maybe you can just Google it out. Example of non-steady state diffusion. There is, but I can't think of at the moment now. But there is. What I know is it is not ideal. Okay, it does happens practically, but most of the time diffusion happens in non-steady state manner. Okay, same goes to the types of diffusion. Okay, you have two types, which is vacancy diffusion and interstitial diffusion. Okay, vacancy diffusion is rare, interstitial diffusion is common. Okay, all right guys, any other questions? Any other questions? All right, now guys, this week Friday I'll be continuing with our lesson for non-steady state diffusion, and then factors affecting diffusion, and also an example. After lecture I'll be having tutorial 1 for the first group. Okay, so I'll be continuing the class directly for tutorial 1. If you look at the timetable, the class for this week Friday is 10:30 till 11:30, and followed by tutorial group T1. Sorry, T2. T2 starts first on Friday, 11:30 to 12:30. So I'll be carry on with the tutorial after the class. Okay. Is it okay with you? So in tutorial, I'll be discussing, and I'll be discussing with you questions on lecture 1 and also lecture 2. But just a rough tips for you. Okay, concentrate more on diffusion. Okay, concentrate more on diffusion. Okay guys, let me stop the recording. All right. If there's no question,